In this video, I'm going to be introducing the concept of related rates. But before we get into any of those story problems or application problems, we first need to be able to derive with respect to time. So that's what we're going to practice in this video. Related rates are derivatives. They're a change in something as time is going by. So a derivative representing a rate of change with respect to time. All kinds of things change as time goes by. But we're going to be abstract in this video, and we're just going to play around with derivatives with respect to time. So given this function, let's find the derivative of y with respect to time. Or in other words, we're going to derive each term individually or implicitly with respect to time. And anytime you're deriving a variable that doesn't match with respect to what variable you're deriving with, we have to multiply by the derivative of that variable. So it's a lot like using the chain rule. So if I derive the y term with respect to time, I get dy dt, or the derivative of y with respect to time. If I derive x squared with respect to time, I get 2x, just this normal derivative, but multiplied by the derivative of x with respect to time. And then lastly, deriving any constant, even if it's with respect to time, is always 0. So now we just want to solve for dy dt. We could just add 2x times dx dt to both sides, and we get our solution. So the change in y with respect to time is 2 times x times the derivative of x with respect to time. It's kind of abstract at the moment, but a change in y could represent a change in height. A change in x could be a horizontal change, and x could be representing a horizontal distance or a horizontal length. So eventually we'll put this to use, and we'll actually apply these terms to a real-life application or a real-life problem. So let's make sure we can substitute values if we're given them. So going back to that last problem, we could evaluate dy dt if we know what x is and if we know what dx dt is. So if we're told that the derivative of x with respect to time is 2 and x is 1, we could just substitute them back into this problem and evaluate the change in y with respect to time. So we're just substituting 1 for x and 2 for dx dt and simplifying, and we get 4. So the change in y is 4 when the change in x is 2 and x is 1. Let's do one more example. Given this equation, and knowing that the change in x with respect to time is 4, let's find the change in y with respect to time when x is 3. Well, first, let's derive implicitly with respect to time. We're going to derive each individual term. So the derivative of y with respect to time is dy dt. The derivative of x to the 4th with respect to time is 4x cubed times dx dt. The derivative of 3x squared with respect to time is 6x dx dt. And the derivative of 1x with respect to time is just 1 dx dt, or just dx dt. So because all three of these terms have a dx dt, we could factor that out. And that leaves behind 4x cubed plus 6x plus 1. Now I can substitute my information in pretty easily. Dx dt is 4, so I'm going to substitute that in right there. And my x value is 3, so I can substitute that in for x. And we can simplify and find out what the change in y with respect to time is given this precondition here. And we could find our solution is 508. So sometimes you could solve for dy with respect to time. Sometimes you could solve for the derivative of x with respect to time. Sometimes you could solve for x. You're just always solving for the variable that you don't know, but you're always going to be given all the other information. So let's do that same problem, but slightly different this time. This time, let's solve for dx dt if we know dy dt and x. So going back to this step right here, and I can just substitute different values in. Now I know dy dt, we're going to substitute 90 there. And this time x is 2, so I'm going to substitute 2 into the two x spots here. We'll simplify this inside and get 45. And now we can solve for dx dt by just dividing both sides by 45 and simplifying, and we get our solution as 2. So the change in x with respect to time is 2, when the change of y with respect to time is 90 and x is 2. So there's a little introduction into finding derivatives with respect to time, and we'll use that in the following videos when we do applications of related rates.